Hello, all of us. We are Group 10 from Division I, and our topic is Instruction Execution Cycle. So, our group members are roll number 53, Prathamesh, myself, roll number 54, Vallabh, 55 is Maitreya, 56 is Abhishek, and 57 is Soham Kature, and roll number 58 is Ajinkya. Today, we are going to discuss this following points, that is introduction, various stages, pipeline processing, interrupts, performance optimization, and some of the examples, and at the end, conclusion. Today, I would like to talk to you about one of the fundamental processes in computer architecture, the instruction execution cycle. This is also known as the machine cycle. In the is a process by which a computer executes a single instruction. It consists of three stages, that is fetch, decode, and execute stage. The instruction execution cycle is a crucial concept in computer architecture, and understanding it is essential for everyone working with the computer system or programming languages. It is a fundamental process that enables a computer to execute programs and carry out tasks. Now let's talk fetch stage. During the fetch stage of the instruction execution cycle, the CPU retrieves the next instruction from memory. This process involves several steps. The CPU first sends the memory address to the memory unit, indicates where the instruction is located in memory. The memory address is stored in a register called the program counter, that is PC. Second, the memory unit retrieve and the instruction from the memory at the specific address and send it back to the CPU. The CPU stores the instruction in the register called the instruction register, that is IR. The PC, that is program computer, is then incremented by the size of the instruction so that it points to the next instruction in memory. The, C- the next step is that the CPU proceeds to the next stage of the cycle, the decode stage, where it interrupts the instruction that was just fetched. The program computer plays a crucial role in the fetch stage because it keeps track of the memory address of the next instruction to be executed. The PC automatically incremented after instructions is fetched, so it always points to the next instruction in the memory. This allows the CPU to execute instruction in the correct order and ensure that the program runs smoothly. Without the PC, the CPU would not know where to find the next instruction in the memory, and the program would not able to execute properly.
Hello, myself Soham Kature. My roll number is 57 from my division, and I am going to explain the decode and the execution stage in instruction execution cycle. The decode stage is the second stage in the instruction execution cycle following the fetch stage, and it is a crucial step in the processing of instructions by a CPU. During this stage, the CPU interprets the instruction fetched from memory during the previous fetch stage and determines what operation needs to be performed. The decode stage involves of various steps. The first step of the decode stage involves breaking down the fetched instructions into its component parts, such as the opcode, which is the operation code, and any other operands that the instruction requires. The second step involves the CPU using the opcode to determine which circuitry or microcode to use to perform the required operation. In the third step, the CPU then prepares the necessary data or memory location for the operation. The last step involves the CPU proceeding to the next stage of the cycle. Once the decode stage is completed, the CPU is ready to execute the instruction. The next step in the instruction execution cycle is the execution stage. Uh, the execution stage is the third stage in the instruction execution cycle. In this stage, the CPU performs the operation specified by the instruction. Once the instruction has been decoded, the CPU fetches any data required from memory or registers and performs the operation. The operation could be an arithmetic or logical operation, a data transfer, a branch, or jump to another instruction, or any other instruction type. During the execution stage, the CPU may also update the program counter, which is a register that keeps track of the memory address of the next instruction to be executed. This ensures that the CPU knows where to fetch the next instruction from once the current instruction has been completed. Once the operation has been performed, the CPU may update the result in a register or memory location, or it may store the result in a temporary register for use in subsequent instructions. After the execution stage is completed, the CPU moves on to the next instruction in the instruction cycle and starts the cycle over again. That's all from me, and thank you.
Hello, myself Abhishek Katore, roll number 56 from Division I. I am going to explain you the topic pipeline processing. Pipeline processing is a technique used by the CPU to execute multiple instructions at the same time by breaking them down into smaller stages. By processing multiple instructions in parallel, it improves the efficiency of the execution cycle by reducing the waiting time for fetching and decoding instructions and data. Let's take an example of a chef cooking a meal. Instead of waiting for each dish to finish before starting the next one, the chef can begin cooking multiple dishes at the same time by dividing the task into smaller stages. This allow them to overlap the cooking process and complete the meal faster. Similarly, we can take an example of a factory. In a factory, an assembly line uses pipeline processing to produce products quickly and efficiently. Each stage of the assembly line focuses on a specific task, such as attaching a part or painting the product and passing it along to the next stage. These allow for multiple products to be produced simultaneously, increasing the overall efficiency of the factory. In the world of computing, basically pipeline processing is a crucial technique used by the CPU to maximize their performance and speed. By executing multiple instructions simultaneously, CPUs can process data faster and more efficiently, leading to better overall system performance. The following block diagram represent the combined as well as the sub-operations performed in each segment of the pipeline. Registers R1, R2, R3 and R4 hold the data and the combinational circuits operate in a particular segment. The output generated by the combinational circuit in a given segment is applied as an input register to the next segment. As you can see here in the block diagram, R3 is used as one of the input register for the combinational adder circuit, and it's also the output for itself. Thank you.
Everyone, my name is Prathamesh Katifiliwal. I am from my division. My roll number is 53. Today I am going to explain you interrupts. So interrupts are the signals sent to the CPU by external device or internal processor that request or temporarily halt its current execution of instruction and switch to a different task or process. When an interrupt When an interrupt occurs, a CPU temporarily stops executing the current instruction and saves its states. When the interrupt handler then takes control of the processor and performs the necessary action to handle the interrupt. Once the interrupt handler has completed its task, the processor returns to the interrupt instruction and resumes the execution cycle from where it left. Interrupts can be caused by a variety of events such as input-output operations, system calls, or hardware errors. They are important mechanisms for following multiple processes or tasks run concurrently on a single processor, as well as for responding to the real-time events in a timely manner. Interrupts can affect the instruction cycle by temporarily pausing it and introducing new code paths, which can impact the program's execution and performance. Thank you.
Hello, myself Maitrey Katkar, roll number 55 from Division I. I am going to explain you the topic performance optimization. Performance optimization in instruction execution cycle involves optimizing the time taken by the processor to execute instructions. This can be done by minimizing the number of clock cycles required to execute each instruction. Caching prediction and branch prediction are two techniques used in computer architecture to improve the performance of processors by predicting the outcome of certain operations and avoiding unnecessary delays. Caching prediction. Caching prediction involves predicting which data a processor is likely to access and storing it in a cache memory. This reduces the time required for the processor to access the data, as it does not need to retrieve it from slower memory locations such as RAM or the hard disk. Cache memory is typically organized in a hierarchy of levels, with the smallest and fastest level storing the most frequently accessed data. Caching prediction algorithm use various strategies to determine which data to store in the cache, including temporal and spatial locality, where data what is accessed is frequently or is located close together in memory is more likely to be stored in cache. Another technique is branch prediction. Branch prediction involves predicting the outcome of a conditional branch instruction before it is executed. This allows the processor to start executing the instructions in the predicted path before the outcome of the branch is known. If the prediction is correct, this can significantly improve performance as the processor does not need to wait for the outcome of the branch before continuing execution. Branch prediction algorithms use various strategies to predict the outcome of a branch instruction, including static and dynamic prediction. Overall, caching prediction and branch prediction are important techniques in computer architecture that can significantly improve processor performance by reducing delays and improving the efficiency of instruction execution.
Hello, myself Ajinke Kaulwar, roll number 58 from Division I. Today I am going to explain examples. So here is the first example of arithmetic instruction. Here is ADD R1, R2 and R3. So we will fetch. The CPU fetches the instruction from memory and load it into the instruction register. Second is decode. The CPU decodes the instruction and determines that it is an add operation on register R2 and R3 with the result storage in the register R1. Execute. The CPU adds the value in R2 and R3, stores the result in R1 and increment the program counter to fetch the next instruction. So this is our second example, logical instruction and R1, R2, R3. First step is fetch. The CPU fetches the instruction from memory and loads it into the instruction register. Second step is decode. The CPU decodes the instruction and determines that it is an AND operation on register R2 and R3 with the result stored in register R1. Third step is execute. The CPU performs a bitwise AND operation on the values in R2 and R3, stores the result in R1 and increment the program counter to fetch the next instruction.
So in the end, we can conclude that the instruction execution cycle is a fundamental process that lies at the heart of the computer architecture. It is the process by which a computer executes a signal instruction and consists of three stages, that is fetch, decode and execute. By understanding these processes, we can gain a deep appreciation for the complexity and power of modern computing systems and how they are able to perform complex operations at lightning fast speed. The instruction execution cycle has evolved and become more efficient over time, enabling the computer to process more data and perform more complex operations than ever before. Ultimately, the instruction execution cycle is a key concept for anyone working with the computer system or programming language and is essential for understanding how computers operate at the fundamental levels. Was about all about instruction execution cycle, and thank you for watching our video.